Hello everyone, welcome back to Algebra. Today we're going to be talking about the first Sylow theorem. I'm going to describe it and then also prove it. And what is the first Sylow theorem is actually a natural question, a follow-up to Cauchy's theorem. Remember that in our previous video, we used group actions, the class equation, to prove Cauchy's. The fact that if you have a finite group and P is a prime divisor of the order of the group, then there is an element of order P. So a natural question is now, suppose G is finite, and we have a power of a prime that divides the order of the group. Well, is there an element of order P to the R? That's not true even for abelian groups. If you have, for example, Z modulo, so if you have Z modulo P cross Z modulo P, then this has order P squared, but there's no element of order P squared. But I can ask, is there a subgroup of order P squared? So the question is, if P to the R divides G, is there a subgroup H in G such that the order of the subgroup is precisely P to the R? That does happen for abelian groups. True if abelian, that's for sure true, because if we have a P to the R dividing the order of the group, then P to the R divides the order of P primary component, and in P primary components we can always find a group of every order dividing the order of the group. So is this true? And it turns out that it is true, and it's a statement of what we call the first Sylow theorem. So let me state it. So let's state and then prove the first Sylow theorem. By the way, the Sylow theorems are named after Ludwig Sylow, Peter Ludwig Sylow, who was a Norwegian mathematician, like Abel was Norwegian. A lot of group theory, great group theory happening in Norway. He was Norwegian, so I believe, in fact, that last name is pronounced Sylow, not Sylow, but many of us, at least in the US, say Sylow, even though it's wrong, but most people say Sylow. Okay, so let me say, what is the theorem? The first, what we now know as the first Sylow theorem, is this sort of extension of Cauchy. Let G be a finite group, and let P be prime, such that P to the R divides the order of the group for some R bigger or equal to 0. Then there is a subgroup H of G with the order of the group H being precisely P to the R. Okay, so this, if R is 1, then this is precisely Cauchy's theorem. So it's an extension of Cauchy's theorem, and it's an extension. It's a natural question to ask if you've just seen Cauchy's theorem. It is also a partial answer to a converse of Lagrange's theorem. So Lagrange's theorem says that if you have a subgroup of a finite group, the order divides the order of the group. But what about the converse? If we have a divisor of the order of the group, then is there a subgroup H of G such that the order of the group is precisely D? And in this generality, it is false. Because, for example, if you consider G to be A4, A4 has 4 factorial divided by 2, so 12. It has order 12, but it has no subgroup of order 6. You can prove that. that there's no subgroup of order 6. So this question is false in general, but if the divisor is a power of 1 prime, then it is true in general. Okay, so let's prove the first Sylow theorem, and you will see that actually we're going to take the proof of Cauchy's theorem and then just generalize it to this setting. So let's see how it goes. So here's the proof of the first Sylow theorem. We're going to do induction. So we know that G, the order of G, is divisible by P, by some power of P. If there is no P dividing the order of G, then we're done. There is the trivial subgroup has order 1. So the order of G will be P times some N, and then we're going to proceed via induction on N. If N is 1, then we are done, because then the order of the group is of order P. Therefore, yes, the only power of P that divides G is 1 or P. But this, if the order of a group is prime, then it is cyclic of order P, and therefore we have the identity, which has order 1, and then we also have the entire group, which has order P, and we're done. So there is a subgroup of every prime power order dividing the order of the group. So now suppose the statement is true for every K, so for every group with order P times K and K in that range, that for any power that divides, any power of P dividing the order of the group, there is a subgroup of that order. And we're going to now suppose that P to the R divides the order of my group. Great. If R is 1, by the way, if the first reduction I'll do is that if R is exactly 1, then we're just saying that P divides the order of the group. And then Cauchy's theorem already tells me that there is a subgroup of order exactly P. So we're going to assume that R is at least 2. And now what I'm going to do is draw the class equation. So remember that G acts on G via conjugation, gives me what we call the class equation, that G is equal, the order of G is equal to the order of the center plus the indices of the centralizers of representatives, generators of the distinct non-trivial conjugacy classes in G. Okay, so there is M non-trivial conjugacy classes. If you take their orbits, then the stabilizers are also called the centralizers, and those indices appear in the formula for the class equation. Okay, so now the first assumption I'm going to make, suppose first, so we're going to do 2 cases. So let me delete this dot and write, there's going to be 2 cases. One, suppose that P does not divide, suppose that there is one of these indices that is not divisible by P. So if P does not divide one of them for some I, so if there is just one I where P is not a divisor of that, then, well, remember that the order by Lagrange, the order of the group is the order of the centralizer at that I, at that xi, times the index of the centralizer. And we know that this is 0 modulo P to the R. And this is, right now, we're saying it's non-zero modulo P, so it's non-zero modulo P, so it's definitely not divisible by p at all. So that implies that, so these two facts imply that this one also has to be 0 modulo p to the r. So that tells me that p to the r divides the order of the centralizer. And again, these centralizers are the stabilizers of a non-trivial conjugacy classes. So those centralizers are, like we proved in the proof of Cauchy, these are non-trivial subgroups of G. Therefore, we have a group which is this centralizer of G, which is non-trivial. The order of the centralizer is divisible by p to the r, and therefore notice that, well, is the induction hypothesis is going to apply for this group because G has order p times n. Let's say it's p to the r times k, because it is divisible by p to the r. And the order of the centralizer, it has to be also p to the r times something other than this k is actually smaller than k, and therefore I can write it as p times p to the r minus 1 times k prime, and this will be p times n prime with n prime less than n, because that inclusion is strict, right? Then the induction hypothesis applies, and there is a subgroup of the centralizer, which in turn is a subgroup of G, with the order of H being exactly p to the r, and we win. Okay, so that is case one, and that was if p does not divide, if one of these is not divisible by p, then we win. Okay, so what happens if then the opposite of this happens, which is all of them are divisible by p? So the second case is, what if p divides all the indices of the centralizers for all 1 up to m, then, well, recall the class equation tells me that this was the sum of this and all the indices. Then now the class equation tells me, well, I know this is divisible by p to the r, so in particular it is divisible by p, and these are all divisible by p also now. Therefore, the order of the center is also 0 modulo p. But then by Cauchy, so that means that p divides the order of the center by Cauchy, or simply because the center is abelian, there is an element of the center of order precisely p in G. Okay, so now what are we going to do with this element? I still don't have, I have an element of order p, but I don't have an element of order p to the r or a subgroup of order p to the r. So what are we going to do with this? I'm going to take n to be the subgroup generated by G. This is in the center, which tells me then that n is normal in G. And now we're going to consider the group modulo n, because this has order. What is the order of this quotient? Will be the order of the group divided by the order of n, which is, well, it is, this one had order p to the p to the r times k, I think we said. This is order p. So this has order p to the r minus 1 times k, or order p times p to the r minus 2 times k. And therefore, the induction hypothesis applies for this quotient. So the induction hypothesis applies to the quotient. And you see that we do have that p to the r minus 1 divides the order of the group. So there is a subgroup, let's call it H twiddle, of G mod n of order p to the r minus 1. And now I want to build back a subgroup of G of order p to the r. How do I do that? Okay, so we have just found that there is a subgroup H tilde in G modulo n of order p to the r minus 1, and I want a subgroup of G. So now consider the map that goes from G to G modulo n, and let H be the full inverse image of that H tilde. Then that is a subgroup of, that is the subgroup actually by the correspondence theorem. This is a subgroup that contains n, and that it maps to, it's the largest subgroup, in fact, that when I map it through phi, I get my H tilde in G mod n. And I claim that H is in fact a subgroup of order p to the r as I wanted. Why is that? So here's the proof of the claim to finish the proof of the theorem, of the proof the induction step, and therefore with induction of the entire theorem, is the following. So consider now the map from H down to H tilde in G mod n. Then we have by, we see that this is surjective, and therefore, so phi of H is H tilde, so this is phi restricted to the subgroup H, and phi of H is H tilde. Therefore, by the first isomorphism theorem, what we have is that H divided by the kernel of that map phi is isomorphic to H tilde. Now, the kernel of this map is precisely, well, the kernel of this map, you see that is n, and n is contained in H, so this kernel is in fact n. So we have that H modulo n is isomorphic to H tilde, and therefore, by Lagrange's theorem, we have, well, by we know what the size of a quotient is. I'm not sure, this is not Lagrange's, it's just the size of a quotient group is the size of H divided by the size of n is equal to the size of H tilde, but the size of H tilde is p to the r minus 1. No, p to the r was, yes, p to the r minus 1. And therefore, the size of H will be the size of H bar times the size of n, which is p to the r minus 1 times p, which is p to the r, like I wanted to prove. This completes, so there is a group of order p to the r. This completes the induction step, and therefore, by the principle of mathematical induction, the theorem holds for all n. And then that completes the proof of the theorem. So that is the full proof of the first Sylow theorem. And as you can see, it is a little bit different But the idea is the same as in the proof of Cauchy, is just use the class equation and use the divisibilities by P of the indices of the centralizers. So let me finish up with an example of the first Sylow theorem. All right, so let's see an example of the first Sylow theorem. So take A5 to be the subgroup, the alternating subgroup in S5. Remember, S5 has size 5 factorial, so 5 times 4 times 3 times 2 times 1, which is 120. So the size of A5 is 5 factorial divided by 2, which is 60, which is 4 times 3 times 5. So the Sylow theorem, the first Sylow theorem tells me that there is going to be a subgroup of order 2, a subgroup of order 4, a subgroup of order 3, and a subgroup of order 5. It doesn't tell me yet how many. That will be the topic of the second and third Sylow theorems, but let's see such examples. So for example, I want a subgroup of order 2. So I can't pick, if I want a subgroup of order 2, I can't pick just, for example, this, because that element is not in the alternating group. So I need something else of order 2, but I can take, for example, 1, 2, 3, 4. That is an element of order 2, and therefore this has order 2, this subgroup. How about order 4? Similarly, I have to be careful. I can't take 1, 2, 3, 4 because that is 1, 4, 1, 3, 1, 2, which is not in A5. So I shouldn't do that. Okay, so instead of that, I'm going to take the subgroup with the identity, and let's say 1, 2, 4, 5. I have here 1, 4, 2, 5, and 1, 5, 2, 4. You can check that this is in fact a subgroup, and it is a subgroup of order 4. This subgroup is isomorphic. If this was isomorphic to Z modulo 2, this subgroup is isomorphic to Z modulo 2 cross Z modulo 2. There is in fact no element of order 4 in A5. Okay, so now how about a subgroup of order 3? For order 3, I can pick the subgroup generated by 1, 2, 3, because 1, 2, 3, it is 1, 3, 1, 2, so it is in A5. So that is a subgroup of order 3, perfect. And how about a subgroup of order 5? For example, I can take 1, 2, 3, 4, 5. That is an element of order 5, so the subgroup generated by it has order 5. And again, notice that 1, 2, 3, 4, 5 is in A5 because it is 1, 5, 1, 4, 1, 3, 1, 2. So it is an even number, has an expression as an even number of transpositions, as a product of an even number of transpositions. So these are all the subgroups that the first Sylow theorem tells me they exist. But the question is, how many are there? What's the relationship between several of them? For example, for order 3, there are others. For example, I can take, well, there's a lot probably, right? I can take 1, 2, 4. That is a subgroup of order 3. So how about that one? Is that one, how is it related to this one? We will see that they are conjugates. So the second Sylow theorem is going to tell me that if I know one, I can conjugate this one and get to any other one of order 3. And the Sylow theorem is also going to tell me how many are there. And in future videos, we'll count how many are there and then find them all. Okay, so I'll stop there. And the next video, we're going to do some more examples of Sylow subgroups, and then state the Sylow theorems, which we will start proving next.